So, hello everyone. It's Sarah back again as your host today, and we're going to tackle week 6. So, well, practically today we're just going to see some questions from, review some sample questions and, discuss. And please feel free to, you know, give me your opinions on what kind of answer you would choose and why, because this is important as it's the way we can figure out how we can reason so we can answer as correctly as possible. So let's get started with the first question. So our first statement is, so you work for a textile manufacturer and have been asked to build a model to detect and classify fabric defects. You train the machine learning model with high recall based on high resolution images taken at the end of the production line. We want quality control inspectors to gain trust in our model. So, which technique should we use to understand the rationale of our classifier? Should we use scaffold cross validation to understand how the model performs on different test data sets? Use the integrated gradients method to efficiently compute feature attributions for each predicted image. Use PCA, principal component analysis, to reduce the original features set to a smaller set of easily understood features. Or use k-means clustering to group similar images together and calculate the Davies-Bouldin index to evaluate the separation between clusters. So, which answer, to you, looks the most probable? And for your information, this is like an explainable AI use case, which means that we want to understand why our model choose a certain prediction. So, obviously, for scaffold cross validation, that's something we use to figure out the performance of a model across different splits. So that's not really helpful to exactly understand why the model choose to predict Y or B. So using integrated gradients is the right way to do it here because we're using images and we would like to figure out which are the features that the model pay most attention to in an image. Using PCA usually is just used to reduce usually the dimension, so it's not going to be very helpful to tell us why the model did what and why. Camis usually is used in clustering. So yeah, it's not going to tell us again why exactly the model choose to predict Y or X. Let's go to the second question. So you need to write a generic test to verify whether dense neural network models automatically released by your team have a sufficient number of parameters to learn the task for which they were built. So what should we do? A. Train the model for a few iterations and check for non-values. B. Train the model for a few iterations and verify that the loss is constant. C. Train a simple linear model and determine if the DNN model outperforms it. D. Train the model with no regularization and verify that the loss function is close to zero. Okay? Remember that usually, like for these kind of tests, two things are actually important. It's reading the question, reading the statement, like the first introduction of the problem well, and then figure out which kind of keywords are important. And of course, like if you're going, like if some of them are similar, you need to figure out what is the difference between two approaches. So in here, for example, the most probable, so the first one is obviously going to be scratch, right? We're not trying to check for non-values, we are trying to figure out if our model is performant enough to learn as much representation from the data as it can. So training the model for a few iterations and verify that the loss is constant. Well, obviously, if our model is learning well, or if it has enough parameters to learn the task at hand, then the loss should actually be, converging to zero. Train a simple linear model and determine if the DNN model outperforms it. If we train a simple linear model, well, A linear model might or might not catch the, non-linearity in the data, especially like usually that's why we use neural networks is to catch the non-linearity in the data. So if we compare it with our model, sometimes like our model may be better than it or worse than it, of course depending on the task at hand. So it's not really very relevant. So training the model with no regularization and verify that the loss function is close to zero, well, that's the most probable. The reason is especially this second section. If we want something, a metric, something that can help us figure out if our model is, learning well, and usually that's either the loss function or the accuracy. Even though it's preferable to check the loss function because sometimes accuracy can be quite treacherous. So training with no organization is just to see, if the model is performant enough without having, without us trying to push it through to learn, force it. So yeah, so D. So your team is using a TensorFlow Inception V3 CNN model pre-trained on ImageNet for an image classification prediction challenge on 10,000 images. You will use AI platform to perform the model training. What TensorFlow distribution strategy and AI platform training job configuration should you use to train the model and optimize for wall clock time? Remember, they asked about TensorFlow distribution strategy and they want to optimize for wall clock time. Okay, so everyone is saying D, right? So first things first, default strategy scratch that because it does not handle distributed training across multiple devices. One device strategy is not what we want because again it does not handle distributed training while they wanted us to use something that handles distribution. So the correct answer is mirrored strategy simply because it can perform distributed training although there is only a single copy of the variables on the CPU host. All right, our next question. So, we work for a maintenance company and have built and trained a deep learning model that identifies defects based on thermal images of underground electric cables. So, our dataset contains 10,000 images, 100 of which contain visible defects. How should we evaluate the performance of the model on a test dataset? A, we can calculate AUC value. B, calculate the number of true positive results predicted by the model. C, calculate the fraction of images predicted by the model to have a visible defect. D, calculate the Gaussian similarity to compare the model's performance on the test data set to the model's performance on the training data set. Choose wisely. So we have a data set that contains 10,000 images and we have 100 of which contain visible defects. The question is how should we evaluate the performance? So obviously we'll have to choose the AUC. So exactly we it's like it's best practices to choose the PR, which is precision recall area under the curve. For the simple reason that it's usually like the best metrics. So usually AUC measures how well predictions are ranked rather than their absolute values. So AUC is also a classification threshold invariant and it measures the quality of the model's predictions irrespective of what classification threshold is chosen. So usually but in most cases, like almost in most cases, especially in research, if you have read a couple of them, we practically always have AUC reported simply because it's not affected by the class distribution. So if we have class imbalance, it's not going to get affected, and it actually takes into consideration two things that we are most of the time interested in, which are true positives and false positives. So, well, in most cases, you will always want to have AUC around. And because here we have a class imbalance, that's why it's more, advisable to use the precision recall AUC. So calculating the number of true positive results obviously will only give us, one view of how the model is doing, and it might actually not tell us exactly if it's, if it's doing a good job at differentiating between the defects and the non-defects. Calculating fraction of the images again will give us only part of the view of what is happening, and then the cosine similarity is usually only used for clustering and, you know more specifically with KNNs. So again, we work for a large institution that is planning to use Dialogflow to create a chatbot for the company's mobile app. So we have reviewed all chat logs and tagged each conversation for intent based on each customer's stated intention for contacting customer service. So about 70% of customer inquiries are simple requests that are solved within 10 intents, which is great. The remaining 30%, though, of inquiries require much longer and more complicated requests. So, which intents should we automate first? So, should we go for A, automate a blend of the shortest and longest intents to be representative of all intents? B, we automate the more complicated requests first because those require more of the agent's time. C, we automate the 10 intents that cover 70% of the requests so that live agents can handle the more complicated requests. And D, automate intents in places where common words such as payment only appear once to avoid confusing the software. Remember that most of the time you don't want to trust the AI to do complicated things for you. All right, nice. Everyone is agreeing on C. That's awesome. So yes, we would want to automate the things that are, well, less complicated for the model so we can cover most of the cases. And for the complicated ones, it is better to leave it for our live agents to take care of it, as as most of the time they are requests that are really complicated. So it's so kind of like trying to figure out the logic behind them and mathematically representing them is going to be way more challenging because they would have very high variability. So we work for a large retailer and we want to use ML to forecast future sales, leveraging 10 years of historical sales data. So the historical data is stored in cloud storage in Avro format. And we want to rapidly experiment with all the available data. So, how should we build and train our model for the sales forecast? Should we A, load data into BigQuery and use the ARIMA model type on BigQuery ML? B, we convert the data into a CSV format and create a regression model and automate tables. C, convert the data into TF records and create a neural model on TensorFlow and AI platform notebooks. D, factor the data into CSV format and use the built-in XGBoost algorithm on AI platform training. Remember, the keyword here is you want to rapidly experiment with all the available data, and the data spans across 10 years. So, which one would you choose? Yes, we would want to use BigQuery because, well, it's not going to give us lots of troubles with the data type. We can throw any kind of data type to it. It will do the pre-processing needed, and we can pick right away the model. That's it. And we can perform our, quick experimentation. Otherwise, if we use any of the other available tools to transform the data and then train, it will take us way a lot more time. And that's something you would want to do if already experimented with very simple models and figured out perhaps you need a more complicated deep learning model. Meanwhile, usually for time series, most of the cases use ARIMA model. So far, it's the best performing model. So we are an ML engineer. We are ML engineers at a media company, and we want to use machine learning to analyze video content, identify objects, and alert users if there is inappropriate content. Which Google Cloud products should we use to build this project? Pops up Cloud Function Cloud Vision API, or PubSub Cloud IoT Data Flow Cloud Vision API Cloud Login, or PubSub Cloud Function Video Intelligence API, then Cloud Login, PubSub Cloud Function AutoML Video Intelligence, and Cloud Login. So which ones? For one thing, Cloud Vision API is for images, not videos. So anything that has Cloud Vision API will go down. So Scratch does A and B. That would leave us with C and D. So for C, what they propose is that we use PubSub. Okay, that's available everywhere, and we need it because we kind of are going to be streaming things, are going to come in real time. So PubSub is very good idea. Cloud functions to handle passing data through several um, tasks that may mean a Vision API and the login. Video intelligence API seems very fitting in this kind of use case because we want to analyze video content. And why are we not using the AutoML video intelligence, second option in D? Simply because they didn't specify anything about they didn't want us to customize anything. They just want to analyze the video content so they can identify objects and alert users if there's any inappropriate content. So it's pretty broad, pretty general. A video intelligence API should be able to do it. But if there was something specific, then we would have to train our own model and then, of course, go for the AutoML option. So we work on a team where the process for deploying a model into production starts with data scientists. It's training different versions of models in a Kubeflow pipeline. So the workflow then stores the new model artifact into the corresponding cloud storage bucket. So we need to build the next steps of the pipeline after the submitted model is ready to be tested and deployed in production on AI platform. How should we configure the architecture before deploying the model to production? So A, we deploy model in test environment. Then we evaluate and test the model. Then we create a new AI platform model version. B, we validate the model first. We deploy model in test environment. Then we create a new API platform model version. C, we create the new AI platform model version. We evaluate and test the model. Then we deploy it. D, we create the new AI platform model version. We deploy the model in test environment. Then we validate the model. A is correct because the model can be validated after it is deployed to the test environment. And the release version is established before the model is deployed in production. B is not correct because the model cannot be validated before being deployed to the test environment. C is not correct also because the model is being set up for the release candidate before the model is validated. Moreover, the model cannot be validated after being deployed to the test environment. D is not correct because the model version is being set up for the release candidate before the model is validated. So that was it. Now about the exam information. So some key facts. So the exam can be taken online or in person. The length, of course, depending on the test site and all of that, countries. So the exam length is 2 hours. You will be having 50 multiple choice or multiple select questions. And you can register at this link. So tips and tricks. So the most important thing to remember about the exam is that it is a practitioner's exam, meaning that you will need to apply your personal experience and knowledge while solving it. So the courses, labs, and the other materials can teach you all about the Google Cloud Platform's products and solutions. But what they are really going to be testing or looking from you is to understand how you can apply all of the knowledge they are providing to real workloads in production. And for that, you will need to draw from your own experience as well. That's why usually, like before passing the test, one of the requirements they have is that you have to have experience. So I'm not sure for you, but at least for me, the things that I don't do so well is read the questions carefully. So read the questions carefully, as there might be hints to the right answer, especially when more than one answer seems valid. For example, you might be asked to provide a solution that minimizes costs, or alternatively, use managed services as much as possible. And this can result in different answers to the same technical requirement. While you're taking the exam, you can also mark questions that you're not sure about and review them at the end. So, next steps is for you to stay on track. So, you can go over week 6 resources. You can share your result on Slack group if you want after you have gone through the PMLE sample questions. And then next week you can take the exam. And good luck. That was it. Thank you, everyone. I hope you enjoyed this and it was helpful somehow.
Thank you for your great presentation, and thank you for joining in this event. It was our last event.
Yeah, I want to say thank you everyone for joining us. It has been a really nice journey, and yeah, share with us question, knowledge, comments, and thanks again
Yeah.
for joining us. It has been amazing.